All right, guys. Well, we're going to do this one more time. I apologize again for being away, but duty calls. So, go ahead and get up your notes. I gave you a new document in eBackpack, which is going to cover 3.3 and 3.4. All right, and when you get that up, we should be talking about the Jovian planets today. So first off, Jovian, as a reminder, is Jupiter-like planet, so it would make most sense to start off by talking about Jupiter, our fifth planet. It happens to be the largest planet in our solar system. Now remember, in the last lecture we said that the Sun makes up a 99.85% of all mass. The next largest thing in our solar system is then Jupiter, and that's 2.5 times more massive than the combined mass of all the planets, satellites, and asteroids that we're going to talk about today. Fun fact, had the size of Jupiter been 10 times larger, we'd actually call it a small star. Now, in the last lecture, I had some music in the background. Today, I'll try and do the same thing. So we'll be enjoying the sounds of Holst's planets. Feel free to go and Google that later on and check it out. There's some great movements. So we'll actually be listening to some Jupiter as we go through. All right, so enough about that. I'll stop nerding out and let's just get right into the lesson. So, as I said, Jupiter is the largest planet. Its revolution, or its time that it's going to take to go around the sun, is approximately 12 Earth years. So the last planet we talked about was Mars, and then we said that was like 2 Earth years. This comes all the way up to 12, and just by stepping on the other side of the asteroid belt. But the fun fact is then that it rotates in less than half the time it takes our Earth. So it's a huge, huge planet, but because it's a gaseous planet, because it's got this really low mass and density, it's able to rotate very, very quickly. So 1 day on Earth is approximately 2.5 days on Jupiter. Also, because of the rotation and the fact that it is, again, a gaseous planet, it actually separates out into different bands based on composition and temperature. So that's why when you look at pictures of Jupiter, and you can look back in your notes where I showed you the pictures of the Jovian planets, you'll actually see that banding effect taking place in there. All right. Now there's a pretty distinct feature on the surface of Jupiter, and that is actually referred to as the Great Red Spot. They believe that it's an anticyclonic storm, and that it's approximately twice as large as our own Earth. Now, when we say anticyclonic, we'll actually talk about hurricanes again, but remember when we talked about a brief introduction to hurricanes because of what's going on, like what you guys see in the news going on in Florida right now, some terrible, terrible stuff. These are cyclones. These are storms that are going to rotate in a counterclockwise direction in the northern hemisphere, clockwise direction in the southern hemisphere. When we say anticyclonic, it means that it's actually clockwise rotating. So anytime you see a picture of Jupiter, always look for the Great Red Spot, and now you have an idea of what's going on there. All right, so I just needed to adjust the screen a little. So the surface of Jupiter is actually like a gigantic ocean of liquid hydrogen. So hydrogen on Earth is usually in the gaseous state, which is what we usually find in our atmosphere. But when we combine 2 hydrogen with 1 oxygen, that's where we're going to get water. Surprise, surprise. Now, we believe that the core of Jupiter and the other Jovian planets is actually going to be rocky and metallic. We haven't actually observed it, right? Just like that mystery box lab, we'll never actually know what's in there. But we have it on pretty good authority based on the densities that they've calculated and the amount of material that has been attracted. We're going to learn about or focus on the idea that the Jovian planets are so large that their mass allows them to attract a large number of moons. Like here we see that Jupiter has 63 moons. So it would then imply that based on Newton's law of gravitation, right, that larger objects with more mass, are able to have a stronger gravitational pull. So there must be something more substantial on the inside of these Jovian planets. Speaking of large mass, large objects, the largest of the 63 moons would be Io, Europa, Ganymede, and Callisto. That would sound familiar because we discussed that those are the 4 Galilean moons. Those are the moons that Galileo was able to observe with his telescope when he was supporting the heliocentric model. But wait, there's more. Jupiter and all the other Jovian planets all have ring systems. Now, the most prominent ring system, yes, is what we see around Saturn. And we're going to talk about Saturn in a second. You can see it right there on the page. We're going to get there. But this ring system is basically this fine dust particle, small planetary material that's stuck in this orbital plane around Jupiter and the other Jovian planets. So I just want to make note of that now, and I'll make a point to highlight it so that you guys remember, hey, if Jupiter has a ring system, and I know that Saturn does, when you see a test question that says, oh, all Jovian planets have ring systems, or give me a unique characteristic to Jovian planets, you're going to think ring system. All right, enough about Jupiter. Let's talk about a planet a lot of people like to make reference to. And that would be Saturn, because Saturn's pretty cool. It's got these tremendous rings. And beyond just rings, fun fact about Saturn is its density is so low that it would actually float in a cup of water, if of course you had a cup that was large enough, or maybe like a solar system sized swimming pool. So just put that in the back of your mind. It was so important that Dr. Seuss mentioned it in his book about the planets. It could always, end up on one of my tests. I mean, I'm not as cool as Dr. Seuss, but I'm trying. Now, again, prominent or most prominent ring system. I just mentioned that. Talking about the density being less than 1, so it would float in water. And then, again, you're going to find these dynamic bands similar to that of Jupiter. Again, differentiating out based on the composition and temperature. Now, a few less moons, so we like to put a number of 61 moons there, and the largest and really the only moon that we would talk about when discussing Saturn would be Titan. All right, so on Jupiter, just to review back, we said that there was Io, Europa, Ganymede, and Callisto. On Tuesday, we talked about Mars having Phobos and Deimos. And then we talked about Earth having the capital M moon. All right, so I just had to adjust my notes. So a little bit more about Titan. It is the second largest moon after Ganymede in our solar system. So just so you guys can put these in order and start to lock in some key details about each one. So second largest, obviously then Ganymede is the largest. And then the last point here is that it too has a cyclonic storm similar to Jupiter's Great Red Spot. We're not really sure why, but these different gaseous planets are getting these swirls or these storms. We'll also see the Great Dark Spot in a minute. So keep this idea going as we try to differentiate between the Jovian planets and the terrestrial planets. All right, so on Tuesday we discussed the fact that Earth and Venus are kind of the twins, right? They're very similar in size and in density, in their location in the solar system. Well, now we're going to the other end of the solar system, right, with Uranus and Neptune, and they too are nearly twins. But Uranus is a little different. And what really makes it different from all the other planets is that it likes to rotate on its side. So if you look back again at the photos in the Jovian section, you'll actually see that the moons are orbiting what we'd consider to be north-south, because the planet itself is kind of on its side. Very cool. So that means, of course, that the axis for Uranus is going to be parallel to the ecliptic. All right, now, period of rotation, 17 hours and 14 minutes. For normal people, that might be about how long you're awake each day. For you guys, especially during the summer, that's probably how much sleep you get. So slight variation there. But revolves every 84 years. And that's a pretty substantial jump from looking at Saturn, right? Saturn was at 29. Now we're jumping all the way out to 84. So it just gives you that idea, going back to Kepler's laws of planetary motion, right? That when we're moving out, although it's a proportional thing, right? That's why you have that fun little math equation in there, because the further we get, it actually exponentially gets larger. So we'll review that a little bit on Friday. So next key factor is the fact that the atmosphere is rich in methane, which actually gives it that bluish color that it's known for. Remember that color is we're seeing it, right, is the energy that the light's emitting, but there's a lot of filtering that goes through the process. So for some of you are like, well, why is it blue? Well, it has to do with the wavelengths of light. All right, and like all of the other planets, it of course has rings. Now, moons drastically less, right? About half as many moons as Saturn, so it's 27 moons. And fun little trivia fact, the 27 moons are named for Shakespearean characters. So if you ever go and play Jeopardy, just remember me when you win, okay? Now, look down there, you got Neptune. This is the 8th and final planet. We can get into that argument another day. I'll explain why Pluto isn't a planet. But look down here, right? It says revolves every 165 Earth days. That's pretty much twice that of Uranus. And then its rotation, 16 hours. So it rotates a little bit faster, but its revolution is drastically longer. All right, dynamic atmosphere, and as I alluded to before, it is home to the Great Dark Spot. Now this is 13 satellites. By that I mean 13 moons, right? Moons are satellites. So it's a good little time to discuss that. And the most prominent one is Triton. So hey, we got another moon we need to know. So the Great Dark Spot, again, an anticyclonic storm. And this is because, hey, Neptune happens to be one of the windiest places in our whole entire solar system. Now, you might be asking yourself, why do we take so many notes on the other planets? But it seems that the amount of information that we need to know gets less and less as we move from Jupiter to Saturn to Uranus and Neptune. Well, I got to admit, we don't know as much about these planets because they're so far away, right? It's only in recent years that we've gotten our different probes all the way out there to send back pictures and help us to better understand what's going on these different planets. The plus side for you, there's less I can ask you about, so I guess we all win somewhere. Before I leave this section, I just want to note that I'm going to leave this video up on my website for a couple days. If I move too fast through something and you're missing a note or two, by all means, please go tap on it later on and just fill in the notes that you're missing. But it's time to move on. All right, so I took a second and adjusted because we're going to talk about small solar bodies. Now you're like, what the heck are small solar bodies? It seems like a lot of words for the other objects in our solar system that are not planets, or the star at the center called the sun. So these are all smaller objects like asteroids and comets and meteoroids. So that's where we're going. Stick with me. Right now, you just need to fill in meteoroid because this definition would have been too long for you guys to write. But an asteroid, right, these are small bodies remaining from the formation of the solar system. As I discussed the other day with the nebular hypothesis, right, the sun formed, all the planets formed, and then there was this like residual material that gravity kind of tethered between the rocky terrestrial planets and the gaseous Jovian planets. These are our asteroids. And asteroids are irregular in shape, right, meaning that they're not perfectly spherical, and they all seem to concentrate in this band right between Mars and Jupiter. Now, every now and then, some of these asteroids will knock into one another and get sent out, and that's some of the reasons why the moon and the Earth have had asteroid impacts. Now, if something like that happened today, obviously we're constantly monitoring the sky, we'd probably know what's coming. So a quick slide change, and there you go. This is what I'm talking about. Right here you got Mars, over here you have Jupiter, and then this whole collection in the middle of material, right? All of this stuff is your asteroid belt. Over here I actually found some photos of asteroids. You can see that irregular shape, right? And they're big chunks of rock just floating out there. All right, I hope that makes sense. I will, of course, review this with you guys when I'm back, but let's keep going. So next we have meteoroids. A meteoroid is a small rock object that orbits the sun, but basically is hanging out in space. Now I point that out because this picture off to the side is going to help us to understand meteoroid, meteor, and meteorite. Out in space, you have your meteoroid, and that's just a chunk of rock hanging out there. When it enters Earth's atmosphere, we drop the oid, and now it is a meteor. The meteor can then burn up in the atmosphere, giving us a meteor shower. If you remember, the actual term for the study of the atmosphere is meteorology. So I'm trying to give you a couple different ways to remember this. And then finally, if that meteor makes it all the way down and strikes Earth's surface, and you can go over and you can pick it up once it cools off, because it's probably very hot initially. But when you can go over and you can pick that up, you have a rock in your hand. And many rocks, as we're going to learn at the end of this trimester, end in ite, I-T-E. So, meteoroid in outer space, meteor in the atmosphere, right, where we have meteorology, and meteorite when you can walk over and you can pick it up. All right, so let's put some notes with this, shall we? I know you're all like so excited. Yeah, I get to write. Don't worry, there's not too much writing on this one. So meteoroid and meteors in general can range from like big chunks of boulder, right, so big that Mr. Weavers wouldn't be able to pick them up, all the way down to just fine grains of sand. Now those fine grains of sand have actually been able to weather down the surfaces of planets that don't have an atmosphere to burn them up. But luckily for us, most of this debris coming into our atmosphere will in fact burn up. I don't know about y'all, but I don't want to be sitting on my couch trying to like relax and boom, there's a big chunk of rock that went flying through. So luckily, like I said, most of it burns up. But we can actually go and find these, right? They can actually find chunks of meteorite, and it's a very popular thing to do if you live up in a glacial environment. Because if you stop and think, something burning up is probably going to be what color? All right, hopefully you all just, thought to yourself, oh, something burning up would probably be black. And on a glacier, it would be primarily white. So there you go. If I want to find a black rock, I want to try and find it on a white surface. And that is exactly what they do. You can actually purchase pieces of meteorite, but scientists obviously want the big chunks so that they can do all kinds of studies. All right, I digress. Let's get to the real point of the matter here. Why do we care about these meteors and the meteorites? Because they're going to give us the information to better understand the formation of our solar system. Right? That's what we've been after in this chapter. We want to understand, how did the planets materialize? What are the commonalities between all of these different planets? And that comes back to looking at the rocks at the core. Meteorites give us some of that information because they haven't been altered by the processes of weathering and erosion, but they're kind of the purest sample that we're going to be able to get to understand how we got to this point. How did our planets form? So that's why meteorites are so important. And we've actually learned so much about them. I know that you guys are thinking, well, this doesn't seem too common. Well, actually, it kind of is. And in fact, right, scientists have classified them into different groups. So we have ones that are more iron-rich. We have a stony category. We have the stony iron mixture, right? When you're like, I'm not sure which it is, we'll just make another category. And then the carbonaceous chondrites. So that's how they break them down. Obviously, each one of these categories give you a lot more information, but we're not going to go into that right now because we got to talk about comets. Now, if I was in class today, I would ask you guys all, what's the most famous comet you guys know about? Some of you are like, I don't know any comets, and that's cool. Some of you are like, I think that was one of Santa's reindeer. And then maybe a couple of you know about Halley's Comet. So let's frame this. A comet is basically a dirty snowball, right? And when I say dirty snowball, I'm talking you're in that snowball fight, right? And your friend's losing. So what do? They go over by the street and they like roll it in all the gravel and they pack it together, and then when they throw it at you, you're like, what the heck, right? I thought we were having a snowball fight, not a snow and rock fight. Well, snow and rock is exactly basically what a comet's made out of. And yes, I'm having a little bit of fun with it. But if you can put that analogy into your mind, a comet is a whole bunch of ice and gas and chunks of rock all mixed together, one big old melange. And this object now is soaring through our solar system, orbiting around our sun, again, very elliptical orbits. But the cool part is that as it's moving around, the sun's radiation is actually blasting or melting, vaporizing the back portion of it. And by the way, that portion of vapor behind it is what we see is that like trailing portion. So we call that the tail of the comet. And you're going to see that in the pictures, that the tail always faces away from the sun, right? Because the rays from the sun are always blasting them off. So the portion closest to the sun that's going to glow, we refer to that as the coma, C-O-M-A, and then the tail coming off behind it. All right, so now y'all are going to have some filling in to do. I'm going to try and point out some of the things I was just talking about, right? The glowing head is referred to as a coma. Some may develop a tail that points away from the sun due to the radiation pressure and solar winds. So the sun's blasting out its rays, and therefore wherever that comet is, the rays are basically going to push that material away. Now, Halley's Comet is in this elliptical orbit that takes about 76 years. All right, so this then brings up the question of where do comets actually like hang out? Right? We talked about asteroids, and asteroids tend to hang out in the asteroid belt. Well, most short period comets will originate and hang out in what we refer to as the Kuiper belt. So that's going to be out beyond Neptune. And when you guys look at the diagrams of the solar system, it's one of those things that you're going to be responsible for. Do you know the asteroid belt? Do you know the Kuiper belt? And I know there is the Oort cloud beyond there, but we're not going to talk about that today. All right. I hope I gave you guys enough time to fill in what you needed to fill in. If not, again, you can always go back and watch this video later on. But it's time to understand why Pluto is not a planet. So, all planets must meet 4 criteria. They must orbit a star. They must have enough mass to be spherical, right? We said that asteroids are not spherical, right? They're irregular in shape. We need an object large enough that it's going to pull in by gravity and make itself spherical. Small enough that it is not a star. Remember, if Jupiter 10 times larger, it'd be a star. So can't be that big. And then has cleared its orbital or its orbit of smaller objects. So I refer to that as the orbital path. And this is where Pluto has its issue. Pluto, being located out by the Kuiper belt, has not cleared its orbital path. So, Pluto, along with about a half dozen others, are considered dwarf planets. So, it's not a moon, has not cleared its orbital path, has enough mass to be spherical, and orbits a star. That is a great description of what's going on with Pluto. And Eris and Ceres, and a couple other ones that we'll get into. So, guys, that wraps up our overview of what a planet is, what a dwarf planet is, what the different Jovian planets are, and hopefully you guys are seeing a nice overview of what's going on in our solar system. Okay, I will see you guys tomorrow. And to whoever is covering my class, thank you very much. I truly appreciate it. Have a great day, guys.